In the previous video, I talked about error analysis and the importance of having error metrics, that is, of having a single row number evaluation metric for your learning algorithm to tell how well it's doing. In the context of evaluation and of error metrics, there's one important case where it's particularly tricky to come up with an appropriate error metric or evaluation metric for your learning algorithm. That case is the case of what's called skewed classes. Let me tell you what that means. Consider the problem of cancer classification, where we have features of medical patients and we want to decide whether or not they have cancer. So this is like the malignant versus benign tumor classification example that we had earlier. So let's say y equals 1 if the patient has cancer and y equals 0 if they do not. We might train a logistic regression classifier, and let's say we test our classifier on a test set and find that we get 1% error. So we're making 99% correct diagnoses. Seems like a really impressive result, right? We're correct 99% of the time. But now, let's say we find out that only 0.5% of patients in our training and test sets actually have cancer. So only 0.5% of the patients that come through our screening process have cancer. In this case, the 1% error no longer looks so impressive. And in particular, here's a piece of code, here's actually a piece of non-learning code that takes this input to features x and it ignores it. It just sets y equals 0 and it always predicts, nobody has cancer. And this algorithm would actually get 0.5% error. So this is even better than the 1% error that we're getting just now. And this is a non-learning algorithm that's, it's just predicting y equals 0 all the time. So the setting of when the ratio of positive to negative examples is very close to one of the two extremes, where in this case the number of positive examples is much smaller than the number of negative examples because y equals 1 so rarely. This is what we call the case of skewed classes. We just have a lot more of examples from one class than from the other class. And by just predicting y equals 0 all the time, or maybe by predicting y equals 1 all the time, an algorithm can do pretty well. So the problem with using classification error or classification accuracy as our evaluation metric is the following. Let's say you have one learning algorithm that's getting 99.2% accuracy. So that's a 0.8% error. Let's say you make a change to your algorithm and you now are getting 99.5% accuracy. That is 0.5% error. So is this an improvement to the algorithm or not? One of the nice things about having a single row number evaluation metric is this helps us to quickly decide if we just made a good change to the algorithm or not. By going from 99.2% accuracy to 99.5% accuracy, did we just do something useful, or did we just replace our code with something that just predicts y equals 0 more often? So if you have very skewed classes, it becomes much harder to use just classification accuracy because you can get very high classification accuracies or very low errors, and it's not always clear if doing so is really improving the quality of your classifier, because predicting y equals 0 all the time is doesn't seem like a particularly good classifier. But just predicting y equals 0 more often can bring your error down to maybe as low as 0.5%. When we're faced with such skewed classes, therefore, we would want to come up with a different error metric or a different evaluation metric. One such evaluation metric are what's called precision recall. Let me explain what that is. Let's say we're evaluating a classifier on a test set. For the examples in the test set, the actual class of that example in the test set is going to be either 1 or 0, right? If there's a binary classification problem. And what our learning algorithm will do is it will predict some value for the class, and our learning algorithm will predict a value for each example in my test set, and the predicted value will also be either 1 or 0. So let me draw a 2x2 table as follows, depending on, and I'll fill in these entries depending on what was the actual class and what was the predicted class. If we have an example where the actual class is 1 and the predicted class is 1, then that's called an example that's a true positive, meaning our algorithm predicted that it's positive, and in reality the example is positive. If our learning algorithm predicted that something is negative, class 0, and the actual class is also class 0, then that's what's called a true negative. We predicted 0 and it actually is 0. To fill in the other two boxes, if our learning algorithm predicts that a class is 1, but if the actual class is 0, then that's called a false positive. So that means our algorithm thought the patient has cancer, but in reality the patient does not. And finally, the last box is a 0, 1. That's called a false negative because our algorithm predicted 0, but the actual class was 1. And so we have this little sort of 2x2 table based on what was the actual class and what was the predicted class. So here's a different way of evaluating the performance of our algorithm. We're going to compute two numbers. The first is called precision. And what that says is, of all the patients where we predicted that they have cancer, what fraction of them actually have cancer? So let me write this down. The precision of a classifier is the number of true positives divided by the number that we predicted as positive. Right? So of all the patients that, we went to those patients and we told them we think you have cancer. Of all those patients, what fraction of them actually have cancer? So that's called precision. And another way to write this would be true positives, and then in the denominator is the number of predicted positives, and so that will be the sum of the entries in this first row of the table. So it'd be true positives divided by true positives. I'm going to abbreviate positive as POS, and then plus false positives, again abbreviating positive using POS. So that's called precision, and as you can tell, high precision would be good. That means that of all the patients that we went to and we said, we're very sorry, we think you have cancer. High precision means that of that group of patients, most of them we had actually made accurate predictions on, and they do have cancer. The second number we're going to compute is called recall, and what recall says is, of all the patients in, so let's say in the test set, or in the cross-validation set, but of all the patients in the data set that actually have cancer, what fraction of them did we correctly detect as having cancer? So if all the patients have cancer, how many of them did we actually go to them and correctly tell them that we think they need treatment? So writing this down, recall is defined as the number of positives, the number of true positives, meaning true positive, meaning the number of people that have cancer and that we correctly predicted have cancer, and we take that and divide that by the number of actual positives. So this is number of actual positives of all the people that do have cancer. What fraction do we correctly flag and send for treatment? So to rewrite this in a different form, the denominator would be number of actual positives is the sum of the entries in this first column over here. And so writing this out differently, this is therefore the number of true positives divided by the number of true positives plus the number of false negatives. And so once again, having a high recall would be a good thing. So by computing precision and recall, this will usually give us a better sense of how well our classifier is doing. And in particular, if we have a learning algorithm that predicts y equals 0 all the time, if it predicts no one has cancer, then this classifier will have a recall equal to 0 because there won't be any true positives, and so that's a quick way for us to recognize that a classifier that predicts y equals 0 all the time just isn't a very good classifier. And more generally, even for settings where we have very skewed classes, is not possible for an algorithm to sort of quote cheat and somehow get a very high precision and a very high recall by doing some simple thing like predicting y equals 0 all the time or predicting y equals 1 all the time. And so we're much more sure that a classifier with high precision and high recall actually is a good classifier, and this gives us a more useful evaluation metric. This more direct way to actually understand whether our algorithm may be doing well. So one final note in the definition of precision and recall. The way we define precision and recall, usually we use the convention that y is equal to 1 in the presence of the more rare class. So if we're trying to detect some rare condition, such as cancer, hopefully that's a rare condition, precision and recall are defined setting y equals 1 rather than y equals 0 to be sort of the presence of that rare class that we're trying to detect. And by using precision and recall, we find what happens is that even if we have very skewed classes, it's not possible for an algorithm to, quote, cheat and predict y equals 1 all the time or predict y equals 0 all the time and get high precision and recall. And in particular, if a classifier is getting high precision and high recall, then we're actually confident that the algorithm has to be doing well even if we have very skewed classes. So for the problem of skewed classes, precision and recall gives us more direct insight into how the learning algorithm is doing, and is often a much better way to evaluate our learning algorithms than looking at classification error or classification accuracy when the classes are very skewed.